All right, folks, it's Bass Action back in action here. In this video, we're going to go through some key skills that you're going to need throughout our year in honors geometry. So these are just some algebra skills that you may or may not feel really comfortable with. And if you need more practice, just let me know. I do have some practice prepared for you, but here I'm just going to go through the steps. The other thing that I want to point out is that if you learned a different strategy that you can do just as effectively, you're welcome to use that. This is just here to help jog your memory on these skills. All right, the first thing we're going to start with is simplifying radicals. Okay, up here on number 1, we're going to start with our simplifying radicals. Now, the method I'm going to show you is what I call the perfect square method, as opposed to doing a factor tree that you might have done when you were first learning how to simplify radicals. This perfect square method is a little cleaner to use. It doesn't take up quite as much space and tends to have fewer errors. Now, in order to do the perfect square method, one thing that I see many students do that's handy is to write a list of perfect squares. Typically, I have students start at 13 squared, so I'll put these up here at the top. So they would say 13 squared is 169, 12 squared is 144, 11 squared is 121, 10 squared is 100, 9 squared is 81, and then you would just keep going all the way on down. So sometimes having this list handy to reference can be useful. All right, what we're going to do is to simplify this radical is we're going to look at the radicand being just the part that's under the radical. And when we look at this radicand, what we're doing is we're going to look for a number from our list of perfect squares that will divide into the radicand without giving a remainder. So we want the biggest number from our list that will divide in without giving a remainder. Now you can use your calculator to find the number just by dividing, but I don't want you to use any special simplifying buttons. So what we can see here was with 75, our perfect square that divides into it is 25. So I'm going to break that down into 25 times 3. That still gives me 75. And then if I have two numbers multiplied under a radical, I can split them into two separate radicals. And then I can simplify. Square root of 25 is 5. This is a much easier way for you to see and remember that these two values get multiplied to give us a 10 in the end. So we can look at another one, 48. If we went through our list of perfect squares, if you had made that list all the way down to 2 squared, which would be 4, you would find the largest number in your list that divides into 48 without a remainder is 16. So we'll have a 16 times 3. Since these are multiplied, I can separate them into their own radicals. Square root of 16 becomes 4, so 3 times 4 is 12, and of course square root of 3 doesn't simplify. I've got one more here. Square root of 242 breaks down into 121 and 2, and so on, and that gives us our final answer. Now, as you get good with this, more often than not, you're probably actually going to skip these middle two steps, and you'll probably find yourself going right from here to here, and that's perfectly fine. The next thing we're going to look at is multiplying radicals, and we'll use some of our simplifying in this process. So to multiply two radicals, we multiply the radicands together. So our 10 times 5 would give us 50. But instead of writing a square root of 50, that sometimes our numbers get kind of big that way, we're going to kind of think ahead. And when I look at this 10, I know that 10 is actually a 5 times 2. So I'm going to have a 5 times 2 and a 5, and that helps me see better that what I'm actually going to get as a perfect square is going to be a 25. So you could just multiply them and do the 50 and go from here to here. Or if you want to kind of think ahead, that's another option. So again, square root of 25 or square root of 25 times 2, this, like we did up here, would split, so I'll end up with 5 radical 2. Now, if you have coefficients on those radicals, the coefficients are going to multiply together to give you an 8, and then again, the radicands multiply. So our 3 times our 6, you could write that down as a square root of 18, or you can think ahead and see that in this 6, you're going to find a 3 and kind of think ahead on what perfect square you're going to end up with. That might make it a little bit easier. Again, you can see I'm starting to skip some of the steps that I did up here on the example 1 problems, because I know that this square root of 9 is going to become a 3 to multiply by my 8 to give me the 24. Last thing we're going to look at in terms of multiplying is squaring a radical. Remember that when you square a radical, or you really square anything, you multiply it by itself. So when we do that, we'll have our 5 times our 5 is our 25. Multiply our radicands together, that's going to give us a square root of 9, which is of course 3. So you're going to have a 25 times what is effectively 3 to give you 75. This is an important concept because we're going to use it for rationalizing on the next set of examples. Now, when it comes to rationalizing, we have a rule in mathematics where we don't leave radicals in the denominator of a fraction. So we always will go through a process called rationalizing. So similar to what we did up above, where if you had numbers that were multiplied under a radical, you could split them, we can do the same thing with division. So if I have a fraction that's under a single radical, I can split that apart into a square root of the top and a square root of the bottom. And you can see that I have this radical 3 over 3 here. And the way this is coming from is that when I take my single fraction and I split it, I can see that I have this radical in the denominator. To get rid of this, I'm going to multiply it by itself, because a square root of 3 times a square root of 3 would give me a 3. But since I did something to the bottom of my fraction, I need to do the same thing to the top. So the square root of 3 times square root of 3 gives me my 3, and then I multiply straight across for the top to get you a square root of 6. So now we've met the requirement. We took care of the radical in the bottom, so we're all done. On the next problem, I've started off with 2 separate radicals, and what I want to call your attention to is kind of look at the values, those 2 radicands, and see that these actually would reduce. So if they are separate, we could write them together. That's the opposite of what I did in A. So I'm going to write this together because now I can see that 24 over 48 is actually 1/2. And then once I get that 1/2, now I'm going to split it again back to the top and the bottom. I see I have a radical in the denominator, so I'm going to rationalize. So radical 2 times a radical 2 to give me a 2. And if I do it to the bottom, I have to do it to the top, and I multiply straight across again. Last one, looking ahead, that's not going to reduce, so I can go straight to rationalizing. Radical 5 times radical 5 gives me 5. Radical 2 times radical 5 gives me a 10. Then the last thing we're going to look at in this video is factoring. And our first 2 examples you're probably very familiar with. Those are going to be our easy ones. And then the next 2 I'm going to go through a process for. So the first 2, when we say with and without a coefficient, okay, with and without a coefficient, what we're talking about is here in front of the x squared terms, okay? Now technically there's a coefficient there. The coefficient is a 1, all right? But if our coefficient is only a 1, as opposed to you can see on C and D where I have a 2 and a 3, our process is easier. We're looking for values that multiply to whatever the constant is and add to whatever the coefficient on this middle or linear term is. So I need 2 numbers that multiply to a negative 21 and add to 4. So you go through your multiplication factors and you come up with 7 and negative 3. Since there's only a coefficient of 1 here, we can take that 7 and negative 3 and drop it directly into these 2 little binomials, these 2 parentheses that have just 2 values in them. Keeping in mind that if you FOIL this back out, okay, if you did all your foiling, you need to always be able to get back to the original problem. Now, when it asks it to factor, we stop right here. This does not equal anything. It's not an equation, so we don't need to, there's no solving. On the next one, I have a similar problem. I'm going to find 2 numbers that multiply to a positive 50, add to a negative 15. Since it's a positive number, I know my 2 numbers have to be the same, and this is a negative, so negative 10 and negative 5. I'm going to just drop those in. The last one we're going to look at are these ones with a leading coefficient. Now you might have another strategy. Guess and check certainly works very well too. And if you have another strategy that you remember, you're welcome to use that. This is just one option and also prepares you a little bit better for some Algebra 2 stuff. So what we're going to do whenever we have a number here on the top is we're going to multiply these two values together, the leading coefficient and the constant, and that's going to give us a negative 24. We're still going to be thinking about adding to that middle coefficient. So I need two numbers that multiply to negative 24 and add to 5. So they're going to be different, and that's going to give us a positive 8 and a negative 3. This method is called split the middle because we're going to take our middle term and we're going to split it using these two values. So positive 5x gets rewritten as 8x minus 3x. And then we keep the other two terms. Then what we're going to do is we're going to factor the greatest common factor. Okay, so we're going to look at these first two terms and say, what do they have in common? They have a 2x, so we're going to factor that out of these two, and we're left with x plus 4. When we look at the next two terms, and we ask ourselves, what do they have in common? We see that they both have a 3, and in fact, we want to factor out a negative 3. Now, this is extremely important that you always write the sign of whatever it is you're factoring out and the value of whatever it is you factor out. At this point, you can see that on this term and this term, they both have an x plus 4. If these two match, then you're good to go. If they don't match, then you either made a mistake or it doesn't factor. Since they both have an x plus 4, I can factor that out, and I'm left with 2x minus 3, and I'm done. I've got one more over here. I've got 3 times 3 is 9 and 10, so we want to multiply to 9 and add to 10. That's a 9 and a 1. You can see I split my middle. Then I went ahead and I looked at my two groups. From the first group, I factored out a 3x, and then from my second group, it looks like they have nothing in common, but they do in fact have a positive 1, so that's what I factored. Notice I wrote the sign and the value. Then I look at my 2, and I see they both now have an x plus 3, so I can factor that out, and I'm left with a 3x and a 1. Again, if you have another strategy that you like, you are welcome to use that. And if you need practice on any one of these skills, let me know, and I have some worksheets for you.